Module landed on Saturday in a volcanic basin close to the moon's south pole and has collected samples of rock and soil. They're expected to be very different from rock formations on the Nearside.
When China's Chang'e 6 spacecraft touched down on the far side of the moon and returned with its first ever samples in June 2024, it revealed some of the moon's deepest secrets. The soil it brought back was unlike anything seen before. Thicker, stickier, and lumpier, its pale surface speckled with bright mineral fragments that hinted at violent collisions and ancient upheavals. These were the sediments of the far side, the part of the moon that does not face our Earth. Buried within these grains were minerals from the moon's deep mantle, likely ejected by the colossal impacts that created the South Pole-Aitken Basin, one of the largest impact scars in the solar system. What China actually found on the moon, and what it plans to do with that information, may seem like the plot of a sci-fi film. Far-side exploration, overcoming extreme challenges. On January 3, 2019, at 10:26 a.m. Beijing time.
Now for an update on China's space exploration program, China says it will launch its Chang'e 4 lunar probe, successful moon landing.
A slender Chinese spacecraft called Chang'e 4 set down on the lunar surface in a way that no human-made machine ever had before. Not on the familiar Nearside that always faces Earth, but on the far side of the moon, the hemisphere that is forever hidden from terrestrial eyes. Its touchdown in the vast von Karman crater, deep within the colossal South Pole-Aitken Basin, would open a new chapter in lunar exploration and redefine the technical limits of what was thought possible in off-Earth robotics and communications. Humanity had seen the far side of the moon before. The Apollo orbiters photographed it in the 1960s, but no mission had ever soft-landed there. The reason was simple and brutal. The moon's unique rotation, locked by gravity in a tidal embrace with Earth, keeps the same face toward our planet at all times. On the far side, the lunar bulk blocks all direct radio contact. Signals that could guide, monitor, or control a descending lander would be swallowed by silence. Without a communications bridge, any attempt to land or operate a robot there was like trying to steer a plane blindfolded. China's space engineers took on the challenge. They solved this problem with a satellite called Queqiao. The name literally translates to magpie bridge in Chinese folklore. Queqiao was launched on May 21, 2018, and sent not into ordinary lunar orbit, but into a halo orbit around the Earth-Moon L2 Lagrangian point, a gravitational sweet spot about 65,000 kilometers beyond the Moon, where the pull of Earth and Moon balance just right. From this perch, Queqiao can see both the far side and Earth at the same time, acting as an uninterrupted relay for radio traffic between Chang'e 4 and mission control in Beijing. Even with Queqiao in place, landing on the far side was no trivial upgrade from a Nearside mission. As Chang'e 4 separated from its launcher on December 8, 2018, it began a carefully choreographed descent that would soon have to proceed without real-time guidance from Earth because of the round-trip delay inherent in relayed communications. As it approached the lunar surface from about 15 kilometers up, the lander autonomously fired its variable thrust engine to slow down from approximately 1.7 kilometers per second, relative speed to nearly zero. At around 100 meters above the ground, it hovered, scanning the terrain with onboard cameras and sensors to measure slopes and identify hazards. After identifying a relatively flat patch in the crater's chaotic geology, it continued its final vertical descent and touched down gently, precisely, and safely, becoming the first craft ever to do so on the far side of the moon. The landing site itself, now famous in lunar exploration history, is a barren but scientifically rich part of the lunar far side, whose geology may tell stories about the earliest solar system impacts and deep crustal materials unseen by Apollo missions. Once its wheels touched the regolith, Chang'e 4 did more than just survive where others couldn't. It immediately began the deployment of the Yutu-2 rover, a small, solar-powered robotic scout, which rolled off the lander platform to begin what would become a long and productive mission. Yutu-2 carries a suite of instruments, but among the most important for understanding the Moon's hidden half is its Lunar Penetrating Radar, or LPR, a groundbreaking instrument that literally sees beneath the surface. Using radar waves that penetrate up to 40 meters below the surface, the LPR has revealed a subterranean landscape that surprised scientists. Rather than a simple, homogeneous layer of dust and rock fragments, the subsurface beneath von Karman shows multiple layers of porous, granular materials interspersed with boulders of varying sizes. This layering likely records ejecta and debris from impacts that occurred billions of years ago, when the early solar system was a storm of meteoroids and planetesimals thrashing through space. The radar data goes beyond mere curiosity. It is the first electromagnetic image of stratigraphy on the Moon's far side, offering a direct look at geological processes that have shaped not only this crater, but perhaps the lunar crust itself. Compared with the subsurface, probed by China's earlier Chang'e 3 mission on the Nearside, the radar results at the Chang'e 4 site show deeper penetration and greater structural complexity, highlighting that the far side has its own unique geological history, likely tied to the immense energies involved in creating the South Pole-Aitken Basin, one of the largest and oldest impact basins in the entire solar system. At night, when the lunar horizon disappears into a frigid darkness, plunging temperatures well below -170 degrees Celsius, Chang'e 4 and Yutu-2 have hibernated and woken again to continue their work. Scientists from the China National Space Administration and collaborators abroad have used every opportunity to sample the Moon's electromagnetic environment, perform low-frequency radio astronomy insulated from Earth's cacophony of signals, and build a picture of how the far side's deep interior compares with the more familiar Nearside. From its halo orbit, Queqiao continues to relay data back and forth more than 65,000 kilometers away from the lunar surface, while Yutu-2 continues to climb over ridges and into craters. But this is only one side of the story. Nearside discoveries and lunar resources. When China's Chang'e 5 lunar mission touched down on the Moon's Nearside on December 1, 2020, in the Oceanus Procellarum region, which is Latin for the Ocean of Storms, this was the first success of its kind after more than 4 decades since the last lunar soil returned to Earth. The probe collected 1,731 grams of lunar soil and rock from a volcanic plain, an area of young mare basalt that had never before been sampled by Apollo or Luna missions. As scientists at laboratories in Beijing, Tianjin, and beyond began opening the sealed sample containers under utmost sterile conditions, they were met with secrets that would reshape our understanding of the Moon's geology and hidden resources. One of the first breakthroughs came in the form of an unexpected treasure, a completely new mineral. Dubbed Chang'e Y, this mineral was identified in lunar basalt particles extracted from the Chang'e 5 samples and certified by the International Mineralogical Association's Commission on New Minerals, Nomenclature, and Classification. Chang'e Y is a phosphate mineral, forming colorless, transparent columnar crystals only microns across. That tiny particle, about 1/10 the diameter of a human hair, was painstakingly separated from over 140,000 other soil grains and then analyzed using advanced techniques like X-ray diffraction. What made Chang'e Y particularly intriguing was not just its novelty, but its helium-3 content. Helium-3 is a rare isotope on Earth, but is hypothesized to exist in greater abundance on the Moon's surface, implanted by billions of years of cosmic processes. Nuclear fusion scientists have long dreamed of using helium-3 as a fuel for future fusion reactors because it produces far less radioactive waste than conventional fusion fuels. While practical fusion power remains a technological challenge, bringing helium-3 back from the Moon marked a symbolic milestone in resource science that had persisted only in theoretical models until now. If a lunar mineral could hold helium-3, researchers reasoned, perhaps there were resources hidden in plain sight, not just exotic isotopes, but water itself. For decades after the Apollo missions in the 1960s and 1970s, the dominant assumption in planetary science was that the Moon was bone dry. The Apollo samples, returned mostly from equatorial Maria, had shown astonishing desiccation with almost no water signatures. But starting in the 2000s, orbital spectrometers began hinting at the presence of hydroxyl, or water signals, at high latitudes, especially near the poles. Yet, until Chang'e 5's return, those had never been confirmed in actual samples. In the summer of 2024, Chinese scientists announced something astonishing. Molecular water, not just hydroxyl remnants, locked within a hydrated mineral discovered in the Chang'e 5 Nearside soil samples. Published in Nature Astronomy on July 16, 2024, the study described a hydrated compound dubbed ULM1, in which water makes up about 41% of the mineral's mass. Unlike water ice, hidden in permanently shadowed lunar craters, this crystalline water was bound tightly in a salt mineral that can survive in sunlit areas of the Moon, even where temperatures swing wildly between scorching by day and freezing at night. The discovery was paradigm-shifting. It demonstrated for the first time in returned lunar soil that water could exist in its molecular form, not just as thin layers of hydroxyl or trapped in glass beads. This water was stable enough in the harsh lunar vacuum because it was chemically bound in a hydrate structure stable at temperatures that at the Chang'e 5 landing site never exceeded about 80 degrees Celsius. Water on the Moon is a potential strategic resource. Future lunar bases, whether robotic or crewed, could use water for life support, radiation shielding, and as a source of hydrogen and oxygen propellants. And unlike ice deep in permanently shadowed craters near the poles, these hydrated minerals in near-equatorial regions could be more accessible for initial exploration efforts. These findings on the Nearside also highlighted something deeper: the hemispherical contrast between the Moon's near and far sides. While Chang'e 5 samples from Oceanus Procellarum revealed new minerals and water, far-side samples from subsequent missions like Chang'e 6 have shown different space weathering features, suggesting the two hemispheres experienced distinct geological and environmental histories. On the near side, older basalt plains and higher heat-producing element concentrations produced extensive volcanic activity and diverse mineralogy. On the far side, rugged highlands and fewer maria have preserved a more primitive crustal record. But the story of Nearside discoveries doesn't end at water and helium-3. Laboratory analyses of Chang'e 5 regolith have detected water signatures in other mineral grains in quantities of tens to hundreds of parts per million. Nuclear fusion potential. The energy prize on the Moon. For decades, scientists have dreamed of a power source that could illuminate entire nations without the carbon footprints and radioactive waste of current energy systems. One of the most tantalizing chapters in that search doesn't lie in Earth's laboratories at all. It lies 384,400 kilometers away on the surface of the Moon. At the heart of that dream is a rare isotope called helium-3, a form of helium with 2 protons and just 1 neutron. On Earth, helium-3 is vanishingly rare. The Moon, by contrast, is believed to hold on the order of 1 million to 5 million metric tons of helium-3 embedded in its soil. That's because the lunar surface, unprotected by a thick atmosphere or magnetic field, has been bombarded for billions of years by the solar wind. This is a fuel source that could one day power cities without pollution or long-term radioactive waste. A fuel that, in principle, could deliver energy equivalent to roughly 50 million barrels of crude oil per ton of helium-3. According to some estimates, 40 tons of helium-3 fused with deuterium, a hydrogen isotope, could supply the entire electrical needs of a large industrial country like the United States for a year. The dream of mining helium-3 from the Moon isn't new. In fact, proposals for lunar extraction date back to at least 1986, when researchers such as Gerald Kolchinsky and colleagues began seriously discussing helium-3 as a potential fuel for commercial fusion reactors in scientific literature. But it was only after robotic missions began returning lunar soil to Earth, most recently China's Chang'e 5 mission.
We're going to have some new moon rocks collected by the Chang'e 5 probe. Chang'e 5 has been the most complex space mission undertaken by China so far. The lander and the sander form the combination that will touch down on the lunar surface to collect samples,
which brought back 1,731 grams of regolith and rock in December 2020, that those proposals gained fresh, tangible grounding. However, extracting helium-3 from lunar soil isn't as simple as squeezing a mineral out of a rock. The isotope is trapped primarily in the tiny glassy coatings and rims on soil grains formed by ancient impacts and solar wind interactions. To release helium-3, lunar regolith would have to be heated to temperatures above about 727 degrees Celsius in specially designed ovens or reactors to drive the gas out of the soil matrix. And then there's the sheer scale of the task. At typical near-surface concentrations of just a few parts per billion, any serious helium-3 extraction operation would need to process hundreds of tons of regolith for every gram of helium-3 obtained. Rough estimates suggest processing more than 150 tons of lunar soil for a single gram of helium-3. That's an industrial challenge on a scale humanity has never attempted off Earth. It demands robotic mining fleets, autonomous processing plants, and energy infrastructure built on the Moon itself, technologies that are only now starting to be sketched out in early research and prototype studies. Why bother? Why dream of such monumental infrastructure? Because if helium-3 fusion ever became feasible, meaning reactors could reliably burn helium-3 with other fuels like deuterium at a commercial scale, the rewards could be about as dramatic as energy innovation gets. Fusion reactions involving helium-3 produce far less neutron radiation and long-lived radioactive waste than traditional deuterium-tritium fusion, and none of the greenhouse gases tied to fossil fuels. It's a vision of near-clean energy, where the raw material for a century or more of power could be scooped from the lunar regolith and beamed, shipped, or otherwise transported to Earth or orbital power stations. This vision places nations at the forefront of a potential future energy revolution. China, for its part, has been explicit about including helium-3 in its lunar resource strategy. Scientists like Ouyang Ziyuan, chief scientist of China's lunar exploration program, have publicly stated that harnessing helium-3 could help provide clean energy for the world, and argued that lunar helium-3 might meet global demand for thousands of years if the technological and economic barriers were overcome.
If we were to mine the Moon for helium-3, we could, at the current level of electricity use in America, or not in America, in the globe, we could power the energy needs of the human race for thousands of years based on the helium-3 that's on the Moon right now.
But beyond science and economics, helium-3 also carries geopolitical weight. Securing access to vast supplies of a potential fusion fuel would position any nation or alliance that achieves it ahead in the next frontier of energy technology. Proposals for lunar infrastructure, such as the International Lunar Research Station planned by China and Russia for the 2030s, argue that building processing plants, habitats, and mining tools on the moon could establish a permanent foothold for lunar industry and shift Earth's energy balance. Dominance on the moon will have ripple effects on the Earth as well. China understands this all too well. Strategic implications for China. What China has done so far can be summed up as building a global map of lunar resources. This is strategic reconnaissance. By understanding where water, helium-3, and other minerals reside, engineers and planners can begin designing the infrastructure of a future lunar economy. This lunar resource intelligence feeds directly into China's broader vision, articulated in joint projects like the International Lunar Research Station, a collaborative effort with Russia, aiming to build a lunar base by 2035 with science labs, energy systems, and long-duration habitation modules. The ILRS plan envisages facilities on the Moon's south pole, where sunlight persists for long periods and water ice may be plentiful. It is being pitched not merely as a Chinese or Sino-Russian project, but as an international platform for lunar science and technology cooperation. Yet these ambitions have clear geopolitical overtones. Space exploration has long been a stage for demonstrating national prowess, from the Apollo landings to the International Space Station. China's rapid progress places it on a trajectory that could rival or even surpass traditional space leaders within this decade. Independent analyses suggest that China might overtake the United States as the top space power in the next 5 to 10 years, if current trends in infrastructure, funding, and launch capacity continue. China's space strategy has been described by its leaders as an embodiment of self-reliance and scientific strength. High-level endorsements, including remarks by President Xi Jinping praising the achievements of missions like Chang'e 6, highlight how space success is integrated into broader narratives of national excellence and innovation. Control of lunar resources, or even the first-mover advantage in understanding and utilizing them, carries implications that stretch from science policy to international economics and security. Water turned into rocket propellant could underpin a cislunar logistics network connecting Earth orbit, the Moon, and Mars. Helium-3, harvested at scale, could one day challenge terrestrial energy markets, and the infrastructure needed to support long-duration missions, such as nuclear power plants, robotic factories, and communication networks, become part of a space industrial base that no longer depends on Earth alone. Yet, these achievements and future plans also exist within a contested geopolitical landscape. China's efforts to build partnerships sit alongside tensions with other space powers rooted in national security legislation and diplomatic competition. Despite obstacles, the sheer momentum of China's lunar program underscores its multifaceted strategic intent, not just to explore, but to utilize and lead. By combining cutting-edge robotics, autonomous navigation, detailed resource intelligence, and grand infrastructure plans, China is transforming the Moon from an inert celestial neighbor into a dynamic platform for science, industry, and geopolitical influence. The lunar surface, once the domain of heroic Apollo images and barren landscapes, is becoming a living laboratory. China wishes to monopolize it, and if it is successful, it will rule the world and the Moon. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.